Okay, we're going to look at problem 2377. So there's a picture, and it says another type of conical pendulum involves two masses. The masses are attached to each other by a string, then passes through a tube. So we're given that M1 is equal to 0.08 kilograms, is spun in a circle of radius 120 centimeters. So right away I'm going to convert that centimeters to meters. So that's why it's good to write down your given, because if you write down your given, you won't forget to do those conversions early on. At a sufficient speed to keep M2 stationary. So this is important because later on when we're summing forces, knowing that this is stationary is going to make a difference. Okay, so A says complete the free body diagrams for each mass. So the easier one is M2. So M2 is like this. I have the weight of M2 going down, which is Fg2, so that's M2G. And then going up, I have the tension. So remember, one rope is equal to one tension. Then for M1, I have the weight going down, so I'll call that Fg1, which is equal to M1G. And then this is the same tension because it's the same rope. The only thing is it's at an angle, and I don't know what that angle is. Okay. So these are the free body diagrams. Oops, I drew this tension the wrong way. Whoops, I wasn't looking closely. So this is the free body diagram showing the forces acting in the direction in which they act. So if this was an FRQ, maybe that's going to be worth 3 or 4 points. You never draw components on a free body diagram, so this is what you're going to do. So part B says determine the centripetal force. Well, if you look at this, the centripetal force is going to be acting towards the center. So first of all, in both of these free body diagrams, I don't know the tension. So if I wanted to find the tension, obviously it's easier to find the tension here because there's only two forces here. So first I'm going to write my sign convention and say summation of f of y is equal to ma. Now this is stationary, so this is 0. And when I look at my free body diagram, I have t minus m2g is equal to 0. Therefore, T is equal to M2G, which is equal to 4 kilograms times 9.8 meters per second squared, which is equal to 39.2 newtons. Then, I want to find the centripetal force. Now remember, you don't draw the centripetal force. Now if I was to sum forces, it's going towards the center, so that's positive. So this is equal to MAC. Now, this centripetal force, this is the net force. Okay? So there's more than one way to do it. The net force, if you look at it, if I drew my free body diagram, remember, my forces, so I can look at this and say, well, what are the forces that are acting in that direction? So I would have the x component of the t. This is t. So this is going to be tx, and this is going to be ty. And I would see that going in this direction, the centripetal force is basically equal to Tx. Now, how could I find Tx? There's more than one way to do it. Now, in the handout and the notes and all that other stuff, I have you finding Tx by saying that this is a right triangle. So instead of me using the Pythagorean theorem to find t, I could rearrange it and say tx is equal to the square root of t squared minus ty squared. So that's one way to do it. So if I do it that way, I could say tx is equal to the square root of t, which I already found here, minus ty squared. But I don't know what ty is, but if I sum forces vertically here, if I sum forces vertically there, I could say that on M1, I could say, well, here's T, here's FG1. I could say summation of f of y, which is MA, and it's stationary. So I could say T minus FG1 is equal to 0. This is TY. So TY is equal to FG1. So TY is equal to M1G. So TY is equal to 0.8 times 9.8, which is 7.84. Then I would put all that in here and say this would be 39.2 squared minus 7.84 squared, and then take the square root of that. Which comes out to be 38.4 for Tx, which is also the centripetal force. So that's one way to do it, okay? Now, for me, remember that when we add vectors head to tail. So remember, here's my tension going like this. And the net force here is my centripetal force. So here's my net force going this way. So remember, when I add vectors head to tail, I get my resultant. So this is my resultant, the net force. So going down here, I have M1G. So instead of doing all this, what I could have just said is that the centripetal force squared, so again, I have a right triangle, is equal to T squared minus M1G squared. So FC is equal to the square root of T squared minus M1G squared. So FC is equal to the square root of 39.2 newtons, which I found there, squared, minus 0.8 times 9.8 squared. So again, FC comes out to be 38.4 newtons. Now, here, this is by using this triangle. Doing it this way, either way that you conceptualize it, this is the normal way that people do it, but you could have also done it this way. The last part, part C, says to find the tangential velocity. So centripetal force is mvt squared over r. So FCR is equal to mvt squared. So when I rearrange the equation to solve for the unknown in terms of the known, Vt is equal to the square root of FCR over m, which is the square root of 38.4 newtons times 1.2 meters divided by 0.8 kilograms. So the tangential velocity comes out to be 7.59 meters per second. And that's it. So again, this is just one type of, and I just want to show you two ways to do it. This is normally what you would do. You would apply Newton's second law each direction. This way, if you have a really good understanding of vectors and how this is the net force and adding my vectors head to tail, again, because you're going to have your right triangle, you can also do it this way. But you have to be very careful because a lot of times on the FRQs, on the AP exam, they're going to look for all these intermediate steps. And someone who's grading it might not understand how to do it this way. And if it's not on the rubrics, you're not going to get credit.